this video I want to show you some actual IR spectra so we can point out the individual regions. And starting with a spectrum of hexane here. And you can see that it looks fairly similar in some respects to the trimyristan spectrum without the ester function. We've got our carbon-hydrogen stretching region up here just shy of 3000 in that kind of 2850 to 2970 range. And we have separate peaks for the methyl and the methylene symmetric stretching here, and for the methyl and the methylene asymmetric stretching. So we've got the symmetric and asymmetric stretching, and then each of those peaks is split into the carbon-hydrogen stretches for the methyl group and the carbon-hydrogen stretches for the methylene. Sometimes it's not clearly resolved the way it is here and the way it was with trimyristan, but you always see that very strong peak just on the low energy side of 3000. And then we have 4 CH2 groups, so we expect a fairly strong CH2 scissor at about 1470, and 2 methyl groups, a reasonably strong CH3 rocking absorption there at about 1380. And then anytime you have 4 or more, we have 4 CH2 groups in a row, you'll typically see a peak around 720 for that CH2N rocking vibration where the individual CH2s are rocking back and forth relative to each other. And then in the fingerprint region here, we have some carbon-carbon stretches and some other bending modes. But there's 4 typical peaks that we usually look at for long-chain hydrocarbons: the CH stretching region, the CH2 scissor, the CH3 rock, and then that long-chain CH2N rocking vibration if we've got enough CH2s in a row. This is a ketone, and you'll see there's a strong carbon-oxygen double bond stretch in the middle of the spectrum at 1715, as opposed to your ester, which was at 1735. So a ketone shows up at a slightly different resonance than does an ester carbonyl. We've got our regular carbon-hydrogen stretching here, kind of those overlapping sp3 and CH3 and CH2 asymmetric and symmetric stretches. And you'll notice we have a sharp peak here at about 3430. This is an overtone. It's a harmonic of this very strong peak at 1715. It's a lot like your musical harmonics. If you have middle C and then you have a C an octave above, right? That's a harmonic. If you hold down, if you're sitting in front of a piano in the atrium of Ham Will, for example, if you hold down the C above middle C and then sharply strike the middle C, you will actually hear both tones at the same time. You'll hear that harmonic. And that's common in guitar playing as well. If instead of pressing the guitar string all the way down to the fret, you just press the string right above the fret and then pluck it, you'll hear that harmonic as well. Right? So that's typical. We expect to see a CH2 scissor, and we do. We expect to see a CH3 rock. We see the CH3 rocking because we both got the CH3s and CH2. And we see a CO single bond stretch because there's an important resonance contributor for the carbon-oxygen double bond that has the positive charge on carbon and the negative charge on oxygen. So you're generally in that 1000 to 1200 region will see a CO stretch, single bond stretch, as well as the CO double bond stretch. Here's a alkene. It's got a vinyl group, right? A CH2CH, that's known as a vinyl group. And so what we're seeing is 2 peaks at 915 and 995. That's typical for a vinyl group. Any other substitution pattern of hydrogens on the CC double bond shows up only a single peak, and we'll see examples of those in a future video. The sp2 carbon-hydrogen stretch is just on the high energy side of 3000, so we see a peak at 3080, and it's always weaker than the sp3ch stretch. We've got a lot of spc3h bonds. We see the symmetric and asymmetric stretching bands there. And then at 1640, we have a carbon-carbon double bond stretch. Right, that's a typical carbon-carbon double bond stretch. This is probably CO2. Well, maybe not. CO2 is usually about there. I'm not sure what this is, but it shouldn't be there. CH2 scissor at 1450, CH3 rock at 1380. Those peaks are almost always present. The alkyne is very distinctive. Nothing else shows up in this region between about 21 and 2200 other than carbon-carbon and carbon-nitrogen triple bonds. So we see that sharp peak. It's typically reasonably strong. It's stronger even for a carbon-nitrogen triple bond because there's a larger dipole difference. And then we see a strong, sharp peak for a CH on an sp hybridized carbon. So this is an sp-CH stretch at around 3300. You'll see in the next spectrum, or maybe two spectra down, that oxygen-hydrogen bonds also stretch about there, but the shape is very different. It's a very sharp peak for an alkyne CH stretch. And then we've got our standard sp3 carbon-hydrogen stretching on the low energy side of 3000. Right? So there's a distinct difference between the low energy side of 3000 for the carbon, the sp3 CH stretch, the sp2 CH stretch at a little bit above at 3080, and then the sp CH stretch at a much shorter, stronger bond at 3300. CH2 scissor here, no CH3 rock, right, because there's no CH3 groups in this molecule. And then there's a peak at 640. That's a bending mode for the alkynes. Typically, we don't even really see that because the salt plates that you run it on often aren't transparent all the way down there anyway. You'll notice the OH stretch for an alcohol is about 3350, in this case 3345, but very different, right? Really sharp peak for the alkyne, broad peak for the OH because of the exchangeable nature of the hydrogen. Standard sp3ch stretches, we've got a nice strong peak at 1070 for the carbon-oxygen stretch of this sp3 carbon-oxygen bond, and then our usual CHT scissor here at 1450. That's typically a fairly strong peak. For carboxylic acid, the OH stretch is really broad and actually generally engulfs the sp3ch stretch that we're seeing. So the sp3ch stretch in this pose shows up at just a kind of hump on top of the broad OH stretch. The carbonyl peak is very strong in about the same region it is for a ketone at 1750, and then we've got the carbon-oxygen stretching for an sp2CO bond here closer to 1200 because an sp2CO bond is a little stronger than an sp3CO bond. But the most distinctive feature of the carboxylic acid is this broad blob that pretty much extends all the way from 2500 to 3500. For aromatics, you would expect to see a sp2ch stretch just up on the high energy side of 3000, which we're seeing here, and then the two methyl groups show up just on the low energy side of 3000, so we can tell we've got both sp2 and sp3 hybridized carbons in there. We've got a decent peak here at 1600 and another one at 1500. That is the benzene ring breathing mode. It's the whole benzene ring expanding and contracting, becoming a larger and a smaller hexagon. Two distinct peaks at 1500, 1600, whereas for a regular alkyne we only see a single peak at around 1650. And then these two peaks down here, these are the peaks that indicate that we have a 1,3 substitution pattern on our dimethylbenzene in this case. Right? A monosubstituted or a meta-substituted benzene ring will have two peaks here, whereas a ortho, a 1,2, or a para 1,4 will have only one peak. And finally we have an amine. This is a primary amine, so it has both a symmetric and an asymmetric stretching, either the two hydrogens going out and in at the same time, or this hydrogen going out while this one comes in. So we see a pair of peaks in that 32 to 3400 range. Right? The secondary amine with a single NH would only show one because there would be no symmetric or asymmetric. And we see a 1600 peak that's broad, blobby in this case, much broader than it would be for an alkyne or an alkene peak in the same region, and that is the scissoring mode for the NH2. Right, the CH2 scissor shows up here around 1450, but the NH2 scissor shows up around 1600. Right, same place roughly as a C double bond C stretch, right, or a benzene ring mode, but it can be distinguished by the breadth of the peak, the large breadth. And then we've got some fingerprint region stuff that's not distinctive. But the nitrogen-hydrogen stretch, about the same place as the oxygen-hydrogen stretch, maybe a little less energetic because the bond is a little weaker. And the type of amine you have is illustrated by whether it's a single peak or a doublet. A tertiary amine, if both of these were methyl groups, there would be no nitrogen-hydrogen stretch, and so you wouldn't see anything in this region.